Earlier on this page, we started talking about projections. We are going to shift gears for this subsection, which is called orthonormal basis. As soon as we turn the page, we're going to take what we talk about here in orthonormal basis and connect it with what we just talked about with projections. So this is a parallel track, and the two will meet as soon as we get to the beginning of page 4. In chapter 2, we talked about a basis of a vector space. A basis, we could think of that as a coordinate system. Every vector in a vector space can be represented as a combination of the basis elements. And that's a way of taking an abstract concept of a vector, and there are infinite vectors in a vector space, and making it a little bit more concrete by just listing the coordinates. We'd like to look at what will happen if that basis is orthonormal, has all these orthogonality properties and the normal properties that we talked about on page 1. Now, most of the time when we think of a basis or a coordinate system, it usually is orthogonal, like the xy axes there. The xy axes, x-axis, y-axis, right angle. So this is a natural thing to think about. We'll start by just looking at some properties of a collection of orthogonal vectors. Just like in chapter 2, when we took a collection of vectors and called them a basis, we put them in the columns of a matrix A, and we said that that vector space is the column space of that matrix A. We want to do that same thing with orthonormal vectors, and we'll call them Qs, and we'll form a matrix that we'll call Q. So now, the first definition there is an orthogonal matrix. Notice that for a matrix to be an orthogonal matrix, it means the columns are orthonormal, not orthogonal. So that's an unfortunate language thing. Orthonormal columns means orthogonal matrix. And orthogonal matrix does not just mean merely orthogonal columns, it means orthonormal columns. Orthogonal matrix means orthonormal columns. The language does not make sense, but that is the language anyways. So good luck with that. That's a tough, tricky thing. So we have this result that from, look at the video clip on page 1 on orthogonal vectors, that if we arrange them into a matrix Q, so the columns of Q are the orthogonal vectors, and take the inner products, all the pairwise inner products, that's like taking those columns and switching them to rows. We said in that video clip that Q transpose Q, the rows times the columns, by virtue of the property of being orthonormal, gives the identity matrix. This is like an equation that represents the definition of an orthogonal matrix. A matrix is orthogonal if its transpose times itself gives the identity. Another way to say that is a matrix is orthogonal if its transpose forms a left inverse. So notice we're saying here that Q transpose Q equals I. We will see as we go through the rest of this chapter that QQ transpose is not necessarily equal to I. Think of how Q could be rectangular. Q does not have to be square. So this actually says something quite strong. A rectangular matrix Q, like if the columns are long but there are only 3 of them or so, if there are a small number of columns but the columns are long, if they're orthonormal, Q transpose Q makes a square matrix, and in fact it's the identity matrix. So again, kind of a strong property, but one that we kind of think about all the time when it comes to orthonormal coordinates or an orthonormal basis. So in working toward an orthonormal basis, we know that one thing that we care about when it comes to this basis concept is not only looking at the span of these columns, or all the vectors that we can generate from these columns Q, but we want to make sure that these columns, in order to call them a basis, we need to make sure that they are independent. So now there's a very nice theorem, the second bold section of this orthonormal basis part on the bottom of page 3. The theorem says that an orthogonal set of vectors is independent. So we get the independence part for free. The proof of that is we know that for the columns to be independent, that's like saying that the null space of the matrix is trivial, meaning that there's no non-zero x that will give us a solution to this null space equation. So in other words, the only x that will satisfy this equation, that qx equals 0, is x equals 0 itself. And you can see by now, watching this video, how this property is used. This defining property is how we conclude that the only solution to this equation is actually x equals 0. It's because this equation is equivalent to the identity times x is 0. Any matrix times 0, any matrix Q transpose times 0 does give 0. So that's the proof that a set of orthogonal vectors is independent. So there's another theorem on there with a string of equalities that I want you to work with other people if you need to, but it's a good exercise for you to see if you can explain to yourself or to others why we can get away with that string of equalities. Each time there's an equal sign at the bottom of page 3. It's because of some property. And so it's a good test to see if you're familiar with the properties, to see why we can go from the norm of qx squared through each one of those steps to the right side of the equation, just the norm of x squared. So that property says that that multiplying by an orthogonal matrix preserves norms. If we have a vector x and multiply by the orthogonal matrix cube, that norm is the same as the original norm of x itself. So work through that. One thing that's not on the handout. The handout is written entirely in terms of real vectors and matrices, which is all we usually use in Chapter 3 and in this semester. But for those of you, especially math majors, who go on to look at complex matrices or matrices with complex numbers, we know that when we take the transpose of a matrix in the complex world, we usually do two things. We take the transpose and the complex conjugate, like put a bar over everything. And so this property translates to q star q equals the identity. So if we have that property q star q equals identity, which is different because it's putting the bar over things, for complex matrices we call this a unitary matrix. And so there's a whole analogous theory for unitary matrices in the complex world as we have for the orthogonal matrices in the real world.